Hello, class. In this lecture, I would like to talk about the amount of energy that can be stored in an inductor, and also finish out chapter 6 by looking at capacitors in series and in parallel, and inductors in series and in parallel, and those are going to be fairly straightforward. All right. What we know about inductors. Well, sort of the opposite of capacitors. V is going to equal my inductance times di dt, right? If you remember, for capacitors, it was I equals C dV dt, and for inductors, it's V equals L di dt. And of course, that is because they're exactly the opposite, right? One starts as a short circuit. A capacitor starts as a short circuit, ends as an open circuit with DC. I'm qualifying this by saying DC. And for an inductor, it starts as an open circuit and ends as a short circuit. And that should tell you that how the current and voltage are going to change in that situation. It's not linear, of course, it's exponential. And we'll look at that when we look at the next chapter, chapter 7. Anyway, so that's one thing. Now, the other thing that I just want to point out is that for inductance, if I'm looking at a coil, a choke, an inductor, all three of those are the same things, as you know. I described that in the last lecture. Inductance, if I wanted to find out the inductance, I would look at the number of turns in the inductor squared. The number of turns, so N equal number of turns in the inductor, right? Mu. Now, when I write mu, I really mean mu equals mu sub r times mu sub o. Just like when I write permittivity. Permittivity is the relative permittivity times the absolute permittivity, right? And we know what the absolute permittivity is. I'll write that up there. We wrote it before in the last one. This is the permittivity of outer space. So everything is related ratially to the permittivity of outer space. And we know the permittivity of outer space. That's a constant that we just keep in our heads forever because it's such an important 8.85 times 10 to the minus 12 farads per meter, right? We talked about that the last time. We talked about epsilon sub r just being a ratio toward that. So it just relates the permittivity of the material to the permittivity of outer space. So for instance, glass has a permittivity of a relative permittivity of 3. There's no units. This has farads per meters. This has no units. All this is really saying is that the permittivity of glass is 3 times the permittivity of outer space. Does everyone see that? This is the same thing. This is permeability. Permeability is to magnetic fields or to magnetism what permittivity is to electric fields. And if you want to learn more about this on the Scott Jen Chris Crenquist YouTube channel that you're going to watch all these things on, there's also a great course for the seniors called Electromagnetic Field Theory. And you can look at those things too. So notice there's no R there, is there? That's right. That means that whatever material is in let's say I've got 2 different types of coils here. I've got a coil, right? And it's just got air in there. That's called an air coil inductor. Now, what if I have that same inductor with the same amount of turns, but instead I was to put a piece of steel in there, right? Steel is to magnetism what copper is to electricity. Steel is to magnetism. Steel is to magnetism. You're thinking, how's he going to fit that in there? What copper is to electricity, steel is to magnetism. Steel or magnetism loves to flow through steel, right? Isn't that why we make all of our motors, electric motors, and electric generators out of steel? That's right. That's why we do it, because steel is to magnetism what copper is to electricity. And so if I put a steel in there, now what is that? What's the relative? If that is steel, I'll put iron, because basically electrical steel is predominantly almost 100% iron. And it's got about 3% silicon in it. You'll get into that when you start to study motors and controls. Anyway, so that's steel. And what is the relative permeability of steel? It's about 1,000, right? Notice there's no units on there. It's a ratio. It's a ratio. So steel has about 1,000 times the permeability of outer space. Outer space, I forgot to give that to you. Mu sub O, another constant that you're going to remember for the rest of your life. 4 pi times 10 to the minus 7 henries per meter, right? Henries are magnetism. Farads are capacitance. Or I should say henries are inductance. Farads are capacitance, but farads are to electric field what henries are to magnetic fields. Okay, you know what I mean. So n squared times mu times the cross-sectional area, right, divided by L. All right. Yeah, I just wanted to check my notes here. I wanted to talk, yes, a little more about permeability. Actually, well, the cross section, let's just draw these two. Let's say that I'm looking at this from either end. It doesn't matter. I'm looking at it from this end. Okay, so I'm looking at it and it's all curled up like that. Coming out the other end. This is going to be your cross-sectional area. Let me get a that's your cross-sectional area right there. Let's just now what's the length? And I think everybody can pretty much see what the length is. The length is just going to be from here to here. That's the length. I didn't draw that well, but you know what I mean. So that's the length, and that would be the cross-sectional area when you're figuring out what the inductance is for an inductor. If you have to make an inductor, right? Let's say that I gave you an inductor and you didn't have anything. You're, in World War II, and you're at Anzio. Actually, that's where the foxhole radio was invented, by the way, Anzio. And so you just have a toilet roll, and you've got wire. And so now you can actually make an inductor so that you can then listen to the armed forces radios broadcasting from offshore while you're getting pounded. But that's where the I'm just saying that's where the foxhole radio came from, and that's how they did it. They actually did get a toilet roll, and they knew what the cross-sectional area of the toilet roll was, and they knew what the length of the thing was. They could change that. They could vary that a little bit. And then they just had the turns, and they used air core. They could even change this and make it into a variable inductor by sliding this steel rod in and out. That's how you tune that inductor, right? To get different frequency radio stations. Anyway, I thought I'd bring that up. That's not something that we're really going to be looking at here so much, except to understand that that's how an inductor is put together. Okay. Now, what I want to do is I want to look at the energy. Right? We know what V is, right? And so, if we know what V is and we know what I is, let's just look at our relationship between power and energy again, right? And we know power is going to be the change in energy divided by the change in time, right? So we know that. We know that that's going to be power. If we want to solve that for energy, then we could say that the change in energy is going to be equal to the power times the change in time, right? And if I wanted to, let me just draw a line along here. Oh, that wasn't too good, was it? So if we wanted to find the energy included in this, that would be the integral of the differential energy, and that would equate to the integral of P times dt. And P, let's see, P is just V times I, right? So that would be the integral of I times V. Oh, we've got V right here. It's just L times di dt, right? Couldn't I rewrite that and say that that is L times the integral of I di, right? dt. What have I got there? P dt, yep. Just a second. Yeah, I was looking at that for a second. I was thinking, hey, there's something wrong with that. I forgot my dt, didn't I? So dt is supposed to be in there as well, and I'm going to put it here too. So, yeah, God, you gotta you gotta follow me on that. And of course, if we were in class, you go to everybody, hey, you forgot the dt there. That's right, of course I did. And of course, I could have canceled it out one earlier, but I switched some things around anyway to make it, I didn't want to lose anybody by taking the constant L out of the integral. It's just a constant. That's just the value of the inductor. So I stays in here in di. And of course, what that gives us is L times I squared over 2, right? And that equals the energy, right? Because I'm integrating the energy. That equals the energy that is stored in an inductor. Using E, maybe I should probably write, well, I like to use E for energy. That's the energy. And we also have another energy, let's not forget, of CV squared over 2. And you're probably, realizing that there's a lot more energy equations out there. They all come to the same thing. They all come back to joules as far as, energy goes. So you've got 2 different energy forms here. We could have energy stored in a capacitor and then shift it over and store it in an inductor. Then we could store it in, kinetic energy, and then we could store it in potential energy, and then rotational energy. You know, there's a lot of energies out there. Let's just write a couple down. So we got E equals mgh, that's potential energy. And we've got E equals 1/2 mv squared, that's kinetic energy. And we've got it equals 1/2 I omega squared, that's rotational energy. And then we've got, I think it's I alpha would be torque energy, right? Alpha would be your angular acceleration. Yeah, so there's a lot of things that, you know, a lot of energies, master them all. Remember, conservation of energy, unless you got a chemical or a nuclear thing going on in there. You know, you can just use the control volume and look at how energy translates from one to the other. Now, what I wanted to do with the remainder of the time is to just talk, and this is really the electronic approach now. Oh, you know, there was one more thing that I wanted to do before I get to the real simple stuff. Why don't I do the simple stuff first? All right. How do capacitors in series add together? Right, I got C1, C2, C3, C4 all together. How do those add up? Okay, if I wanted C equivalent of those four in series, let me write it this way. 1 over, just like resistors in parallel, C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4. Does everyone see? And that's for series capacitors. So it works exactly opposite of resistors. All right. Now, how about if they are in parallel? So I've got now the same one, same capacitors. So this would be just like, of course, resistors in parallel. And so these in parallel, C equivalent is just C1 plus C2 plus C3 plus C4. Right, so very, very easy to see how to add those. They work exactly opposite to resistors. And hey, what do you know? When we look at inductors, 1, 2, 3, 4 inductors, L1, L2, L3, L4. These work just like resistors. So L equivalent for those in series is just L1 plus L2 plus L3 plus L4. All right. And then the other one, if they were in parallel, not going to take up too much room if I can help it. And again, this is just L1, L2, L3, and L4. If I was to add these up, then 1 over L equivalent, just like resistors, is going to be 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over L4. All right. So inductors are much the same as resistors as far as adding in series and parallel. Capacitors are exactly the opposite to that. So just, like I say, that's about the easiest thing in this chapter that I got to, could I do things like having capacitors in series parallel and then figuring them out? No, it's just backwards, guys. You're all college students in engineering. I don't think it's I don't think it's a problem as far as adding these up, putting circuits together, figuring out what the equivalent inductance is, and all of that in DC. In the next chapter, we're going to look at step functions and turning these things on and seeing how they charge over time. But that's not this. What I do want to point out, though, and like I'm saying, I'm sort of taking you ahead on a tangent as to what is the importance of these two constants that you're going to memorize for the rest of your life. I mean, we all know that Euler's constant, right, is 2.71828. And we know that pi is 3.14159. That's right. If you want to roll that to 1/6, I could go for that, right? But I go with 159 because 1415, it just makes sense. Just sort of rolls off your tongue, doesn't it? 1828 sort of rolls off your tongue. Well, those are constants that you remember. And of course, you remember that the charge, right, on an electron, because you're electrical engineers, is minus 1.602 times 10 to the minus 19 coulombs, right? These are all things that you commit to memory. These two things are going to be committed to memory now for the rest of your lives because you're electrical engineers. Epsilon sub 0, 8.85 times 10 to the minus 12 farads per meter. Mu sub 0, 4 pi times 10 to the minus 7 henries per meter. Why is that so important? Let's do this. What is the square root of 1 over mu sub 0 epsilon sub 0? Right? Plug that into your calculator. You're going to plug it into your calculator at the same time I'm plugging into my calculator, and we'll see who can calculate better. Oh no, there's a lot of people that will do this and get a different answer than I'm going to get. Which may be the right answer, but I know what the right answer is. So if I don't get that answer, I'm going to go back. I'm not even going to tell you that I've calculated it. All right. Yep, I did get the right answer. What do you know? 299.9394 times 10 to the 6th. And what are my units? What are my units? Didn't I say it was farads per meter and henries per meter? What is a farad per meter? Let's see, a farad per meter. That would be an amp squared seconds to the 4th divided by a kilogram meter squared divided by a meter. Right? So wouldn't that be an amp squared seconds to the 4th over a kilogram meter cubed? Does everyone see that? Okay, now, what is a Henry per meter? Well, I'll do it over here. A Henry per meter would be a kilogram meter squared over amp squared second squared, that's a Henry, divided by a meter. So that would be a kilogram meter squared divided by Oh, I'm sorry, not a meter squared. Get my, because we canceled that meter out, right? You're probably all saying that right now. Oh, he canceled that meter out. Oh, figured that one out. Right, because that cancels, of course, with that over amp squared seconds squared. Now, let's stick that in our thing here, right? Don't we just have a fraction? We're going to put that in here. So I've got, the first one is henries per meter, but the henries are on the bottom, right? So I have to reciprocate this. So that would be a kilogram meter per amp or amp squared second squared, right? And then what's the other one here? Well, we've got that on the bottom too. So I've got an amp squared seconds to the fourth. I've got to reciprocate that over a kilogram meters cubed, right? And it's all taken to the square root. That's right, to the 1/2. 1/2 is the square root. If the exponent 1/2 there, the same thing as writing the square root radical sign. I think everybody knows that. All right, so we know what that is, but we would like to find out what the units are for this magical number that we've got, 299 million what? Let's start canceling some things. Let me get my red pen. Well, we've got amp squared, those cancels with amp squared. I've got kilograms, those cancel with kilograms. I've got meters, and those cancel with one of the 3 meters, leaving 2 left, right? And I have seconds squared, and those cancel with all but 2 of the seconds. So what I have is I have meters squared per second squared taken to the square root. Meters per second equals the speed of light. See how important these constants are? See how important these constants are in your life as an electrical engineer? So, well, I was pretty long on the last couple things. We can do another thing too. I'm not going to do it, but I just want to point it out to you because I don't really have a lot of things. But what if instead of the square root of this, what if instead I had the square root of mu sub O over epsilon sub O? What's that? That's the characteristic impedance of outer space. That's the impedance sign. Characteristic impedance of outer space. What is the characteristic impedance of outer space? Let's just cut a hole right here. 377 ohms. Z sub 0 equals 377 ohms. So not only does this tell us what the speed of light is, it also tells us what the impedance of outer space is, right? And of course, the impedance of outer space is the impedance of the atmosphere too, because both of these are very close to the same constant in the atmosphere. For air, mu sub r is very close to 1, and epsilon sub r is very, very close to 1. So when we're broadcasting microwaves through the atmosphere, we're looking at an impedance that we're broadcasting through of 377 ohms. That becomes more important when you're looking, later on, you'll be taking electromagnetic waves and stuff. All right. So I hope everybody had a good time with the lecture today, found out where the speed of light came from and why it's so important that we know that. And it's also been a good, introduction to permittivity and permeability. Permeability is to inductance, what permittivity is to capacitance. See you in the next lecture.